Hello everyone. Before diving into today's topic, we want to take a moment to thank you for your support. Every like, comment, and subscription truly makes a difference and helps this channel grow. If you enjoy our content and don't want to miss our upcoming videos, subscribe to the channel and activate the bell to receive all notifications. What is light, really? A spark that cuts through darkness, a caress that travels through the void, or perhaps one of the universe's most mysterious keys. For centuries, humanity has tried to understand it, categorize it, reduce it to formulas. But every time we thought we had grasped it, light changed its face, revealing new surprises. This is how one of the most fascinating revolutions in physics began, the one that led us to discover that light, the same light that passes through our windows or refracts in rainbows, is actually made of tiny grains of energy called photons. At first, though, everything seemed clear. Light was a wave. An electromagnetic wave, to be precise, similar to sound waves or ripples on a pond. It propagated through space by oscillating with well-defined frequency and wavelength. Everything made sense, until some experiments started telling a different story. One of them was the photoelectric effect experiment, a seemingly simple phenomenon. When a metallic surface is hit by light, it emits electrons. But the details of this phenomenon were anything but simple. According to classical physics, the energy carried by a light wave should gradually accumulate in the electrons of the metal. The more intense the light, the more energy available, hence more electrons emitted. But that wasn't the case. In the lab, it was observed that low-frequency light, like red light, didn't free a single electron, no matter how intense it was. On the other hand, ultraviolet light, even if weak, caused the immediate ejection of electrons. There was no gradual accumulation of energy, no waiting. As long as the light had the right frequency, electrons would shoot out instantly. This result shook the very foundations of wave theory. Why should frequency matter more than intensity? Why would seemingly higher energy light be less effective than colder but more intense light? Something didn't add up. Classical physics was powerless in the face of this experimental data. It was time to look further. A radical solution was proposed by a young Albert Einstein. Building on an intuition by Max Planck, Einstein suggested that light was not simply a continuous wave but was made up of discrete packets of energy. He called them quanta of light, today known as photons. Each photon has energy proportional to the light's frequency, according to the formula E equals hf, where h is Planck's constant and f is frequency. In other words, each photon is like a bullet of light. If it has enough energy, it hits an electron and instantly ejects it from the metal. If it doesn't have enough, nothing happens, no matter how many bullets are fired. This view changed everything. Energy was no longer something continuous and diffuse but discrete, quantized. The microscopic world obeyed rules completely different from those of the macroscopic world. And light, that familiar phenomenon, revealed itself as a dual creature, both wave and particle. The discovery of the photoelectric effect was not just a curious experiment, it was the spark that ignited quantum mechanics, one of the greatest scientific revolutions of the 20th century. Thanks to this work, Einstein was awarded the Nobel Prize in Physics in 1921. But it didn't stop there. Another experiment, conducted by Arthur Compton in 1923, offered even more concrete confirmation of the photon hypothesis, the Compton effect. In this experiment, Compton bounced X-rays, extremely high-frequency light, off nearly free electrons. The photons, upon hitting the electrons, changed direction and lost energy, exactly like bullets rebounding after a collision. The frequency of the reflected light was reduced, consistent with the loss of energy. A behavior impossible to explain with classical wave theory, but perfectly understandable if light is made of particles with momentum. It was the definitive proof. Light behaves like a particle. And yet, light also continues to behave like a wave. It can interfere with itself, diffract through a slit, and create interference patterns on a screen. This is the mystery of wave-particle duality. At the quantum level, elementary particles like light, but also electrons, are neither waves nor particles in the classical sense. They are both and neither. They are quantum entities that manifest in different ways depending on how we observe them. This concept shattered every human intuition, forcing us to rethink reality itself. In quantum mechanics, what we observe depends on how we observe it. But these abstract concepts haven't remained confined to laboratories or university classrooms. Applications of the photoelectric effect are everywhere in our daily lives. Photovoltaic cells, for example, exploit this very effect. Sunlight hits a semiconductor material and frees electrons, generating electric current. This is how we can produce clean energy from the sun. Digital camera sensors detect photons and transform them into electrical signals to create images. Even remote controls, barcode readers, optical fibers, X-ray telescopes, and even CT scans and laser treatments in medicine are based on principles related to the quantum behavior of light. All of this began with a mystery. Why does light hit metal that way? And from that seemingly trivial question came a new way of understanding the universe. Light is no longer just what illuminates, it's a quantum messenger, an invisible river of particles traveling through space and time, carrying with them information, energy, and even unsolved mysteries. Understanding the nature of light has driven us to rewrite the fundamental laws of physics, to conceive a world where reality is made of probabilities, not certainties, and where every particle can be anywhere, until we observe it. Einstein himself, despite helping lay the foundations of quantum mechanics, was troubled by it his entire life. His famous quote remains, "God does not play dice with the universe." And yet, quantum physics shows that sometimes, it's precisely those quantum dice that allow us to see deeper into the structure of existence. So the next time you see a ray of sunlight filtering through the leaves or a light bulb turning on in a dark room, remember, you're witnessing something infinitely deeper. Every photon that touches your skin is a fragment of the universe, a particle of light that has traveled for billions of years to fulfill its small, extraordinary destiny. Light is not just what illuminates. It's what reveals.